Okay. So our main presenter tonight is Don Cooper, who was basically involved in the NASA moon moon program, Apollo moon program. Worked at is from Oklahoma. It's a native of Oklahoma. Majored in physics and mathematics at Oklahoma Baptist University. Worked at George C. Marshall Space Flight Center, and then later at the Johnson Space Center in Houston. And was basically one of the key guys involved with getting us to the moon. So he's a real treasure, and we're really appreciative to have him here tonight as our guest speaker. And he'll be talking about the calculations that got us to the moon. He retired in 2002 and found a new career teaching about the Apollo moon missions and the importance of mathematics. So I want to welcome Don Cooper. Welcome, and you can begin your talk.
Okay. Well, thank you. I know that we always have mathematicians here, so I try to be on my toes the best I can.
Hey, Don, we're not sharing the screen.
Oh,
Yeah, we want to share the screen.
is that it?
Yeah.
Oh, okay.
Easy to share it with the Zoom.
Here we go.
Yeah,
I have two talks that I give. Of course, COVID really slowed me down for schools, but I would normally go around to a lot of schools, and I would give my first talk, which would be how we went to the moon and back, and demonstrate that. But then, if I got a chance to go to the AP Calculus classes, I would do my favorite talk, which is the one tonight, about the mathematics of how we get to the moon. As you mentioned, 2 days after I graduated from college, I got in my car and drove to Huntsville, Alabama, and went to work for the Army. We designed a new missile in 1 year, and then I transferred to NASA. And tennis has been a theme that's run through my life. I got on the Huntsville tennis team, and at the end of the first year, my doubles partner turned around and said, "How would you like to work for NASA?" 2 weeks later, I was working for NASA in a building just across the street from where I worked at for the Army, both on Redstone Arsenal in Huntsville. But so Apollo guidance. Go ahead.
Next slide.
Yeah.
We'll go to the next slide.
This is a Saturn V rocket on the way to the moon, and you can see right here at this black circle right here at the top. That's where the computer and all the intelligence is to control the Saturn V vehicle on the way to orbit and to get out of Earth orbit going to the moon. Go ahead. Right here is a picture of one of the F1 engines at the first stage of the Saturn V. And right here, you notice there's 3 struts, and it fastens this device right here at the end, and then the other end fastens to the structure of the Saturn V. And this is called an actuator, and it can move in and out. And by moving in and out, it can actually turn the direction that this engine faces and change its thrust. And that's how the Saturn V vehicle is controlled in the first stage, and even in the second stage, also in the third stage. It's all done like this. Okay, so what do we know if we're going to develop some equations that's going to guide this vehicle towards the moon? What do we know? Well, we know the weight, the thrust, where we want to go. We have computer simulations that we can run and take a look and see what's happening. And we also know the position, velocity, acceleration, and time at any instant that this vehicle flies through the air. So the first thing you would ask, how do we know that? Well, on board the Saturn V is an inertial platform. And this is a representation of it. And this inertial platform, but represented by the white platform here, has 3 gyroscopes on it that are perpendicular to each other, and when they spin up, they keep this platform absolutely in the same place. The outside of this is fastened to the structure of the Saturn V. So when the Saturn, and then there are 3 accelerometers measured, located right next to the accelerometers, and so they can measure acceleration. And so when the Saturn V lifts off, it goes up, It then rotates to point number one pin down range where it's going to do the tilt program, and then it tilts like this. But the whole time, this platform stays exactly in the same orientation. It's aligned to within 1/1000th of a degree prior to liftoff, and it stays within about 0.05 degrees for the next 6.5 hours. This is a picture of it. It's a little bit bigger than a basketball. It's called the ST-124. The reason why it's called ST-124 is because the first 123 didn't work right. And so this leads me to my first joke, that if first you don't succeed, try again. Well, that applies to most everybody but paratroopers. Anyway, but this is what it looks like. Very complex instruments. The bearings are actually liquid helium, and they reduce its friction to almost zero. Go ahead. This is what it looks like going into orbit. First stage takes off at maximum dynamic pressure is at about 6 miles, about 1 minute and 23 seconds after liftoff. And then the first stage runs out of fuel at about 2 minutes 41 seconds. We're 36 miles high, so we're pretty much out of the atmosphere. And then the second stage ignites, and it starts. And shortly thereafter, the guidance system takes over, which is in the onboard computer. Up until this time, the tilt program is predetermined based on time, and it simply controls the vehicle to tilt over at a certain rate. After that, it's active guidance that guides it on into orbit until it gets to 100 miles above the Earth, and it's traveling at about 5 miles per second. And it takes about 12 minutes to get to orbit. Every rocket that goes to Earth orbit follows a path similar to this. And the reason why is because this is the path that will get you there using the least amount of fuel. And then once we're in Earth orbit, we make a couple of resolutions to check out all the instruments and computer things. And if everything is okay, we reignite the third stage and increase our speed another 10,000 feet per second in order to reach escape velocity. If you want to see escape velocity, look at this guy's shirt. He's ready to go. So what are our variables? Well, they're kind of like what we know. Weighs about 6 million pounds, but we don't know just exactly what it's going to weigh at liftoff. And the same thing with the thrust. All these stages have been test fired prior to putting them together at the Cape and lifting off. But once they lift off, they're going to run at whatever thrust that they're going to run at, which is going to be close, we hope. And one of the other things that guidance equations have to take care of is that the Saturn V is designed such that if any one engine fails, then all the fuel is diverted to the other engines and it continues on to burn. And if it doesn't happen right after liftoff, it can still make the mission. And that actually happened on 2 missions. Apollo 6 had 2 engines out, and Apollo 13 had 1 engine out in the second stage, and made it to orbit and successfully. And out of plane, we're not going to fly just in one plane. We may have to divert into a different plane. Mixture ratio shift. Mixture ratio shift came about because the Johnson Space Center had to guarantee what the maximum weight would be of the command module for the astronauts were in. And it seemed like about every year they would increase the weight until finally those of us at Marshall Space Flight Center in Huntsville, Alabama had to figure out how to make the Saturn V put more weight into orbit. And the way it was done is that acceleration looks like this. And however, when you get out of the atmosphere, the ratio, on the second stage, the ratio between liquid hydrogen and liquid oxygen is an optimum amount when you're at sea level with the atmospheric pressure pressing on you. But however, when you get out of the atmosphere and the atmospheric pressure disappears, then the ratio of fuel between liquid hydrogen and oxygen can be changed in order to increase the amount of thrust that you can get out of the vehicle. And that's called mixture ratio shift. And what it looks like acceleration-wise is this. Something like this, is that there's going to be a period where acceleration is going to decrease while it's making the shift, and then it's going to increase again. And the net result is that you're going to end up, and I probably should have drawn this a little bit better, more like that, you're going to increase with acceleration going up faster than it would otherwise. And so you can put more weight into orbit and towards the moon. About, I think it's 30 or 40 seconds before cutoff, the control system people decided that they were going to shut down the inboard engine. There's 5 of them. And let me show you what that looks like. This is the Saturn V here. I do this, this gets the kids' attention. And here are the computers and things here at this end. And I'll just go ahead and take this apart. They both look the same. Let me do this. You can see the 5 engines here, and the inboard engine is the center one, and that's the one that shut down early, and that leaves the outer 4 to go ahead and fly the vehicle. It makes for a smoother shutdown when it shuts down. And there's going to be a 10-second period where there's no acceleration while the separation occurs, and that's got to be taken into account with the guidance equations also. Go ahead. So to start this whole process, we'd say, well, what result do we want? Well, we know we want to go into this 100-mile orbit, and we want to go in there at a certain altitude and a certain direction and a certain plane. And so what coordinate system do we want? Well, the inertial platform has a coordinate system. And that coordinate system is this. If you take the Earth, the center of the Earth, and draw a straight line, that'll be the y coordinate through the launch site. And then you take a tangent to that perpendicular downrange in the x direction, and that's your x coordinate. And this is the coordinate system of the inertial platform. And then there is a z direction also, which we won't talk about much, but this has to do with the out of plane direction. And so therefore, we're going to fly the vehicle. Our acceleration is going to be somewhere in this coordinate system. And this angle right here we'll call high pitch. Now the reason why we have to take into account the outer plane is that simply because this is the Cape here on this Earth picture. It looks kind of like a tennis ball, but really it's the Earth. This is the Earth right here, and this is the plane we want to go into. And this plane is defined by the center of the Earth, the center of the moon, and the landing site at the moon when we get there 3 days later. So everything is projected forward mathematically. And then you can define this plane. And so therefore, when we lift off, we want to lift off and to get into this plane around the Earth so that when we do our burn out of Earth orbit, we don't have to do a plane change. And neither do we have to do any plane changes all the way to the moon to the landing site. So we've done all the heavy work back here and let the Saturn V do that. Now there are 3 mid-course corrections that are built into the mission that can correct anything that's not as perfect as we want it to be. One of them was always used, the other 2 were never used. So as time goes on and it's sitting on the launch pad, you can see there's an optimum time to launch to get into this plane with minimum fuel. However, as we've seen many times, the launch vehicles don't necessarily lift off exactly on time. So the Earth continues to rotate, and lo and behold, we're behind the plane, so we have to fly back into the plane And later on, we had to fly back further into the plane until finally we get out of our allowable range for using up our fuel, and we have to delay the launch time. How long? 24 hours, because the Earth's got to rotate one time. Now you know what a launch window looks like. The launch window is about 4.5 hours for the Saturn V. Most vehicles that launch from the Earth, that's what their launch window looks like. It's something like 4 hours. After that, you might as well turn off the TV. They're not going to launch that day. So, go ahead. I'm going to add just a little bit of history to this. Back in 1960, in Huntsville, Alabama, we were responsible for the guidance equations for the Saturn V. Just like Johnson here in Houston was responsible for all the equations that were on the command module for the astronauts. And so, question was, how were we going to fly this thing? Well, there was a PhD mathematician that had been assigned the job named Dr. Hopner. He had worked with Werner von Braun, who was the head of Marshall Space Flight Center. You might remember von Braun. He was the guy that developed the V-2 rocket in Germany in the Second World War and launched 3,000 of them, 1,000 towards London and 2,000 towards Antwerp before the end of the war. And he came to the United States, and by 1960, he was appointed head of the Marshall Space Flight Center in Huntsville, Alabama, and given the job to develop the Saturn V vehicle that would get us to the moon. And so here we are, and Dr. Hopner worked for him in Germany. The entire center was run by Germans. All second-level managers were German. They all had the most experience in building rockets, and so it was a natural thing to have happen, although it wasn't publicized an awful lot. And I was at the bottom, and the Germans were at the top. Okay, so Dr. Hopner's approach was to use calculus variations and to run all the simulations using calculus variations and then perform partial derivatives of all the variables that could possibly happen during the flight, and then incorporate all that into a polynomial and put that polynomial in the computer. And then no matter what happened, you would feed in the position, velocity, acceleration, and time from the inertial platform, and then it would pop out with chi pitch, which would be a vector. And that's the direction you want to fly. And did that work? It did. And it worked very well. But it had one flaw, is that it took about 3 months to develop one polynomial. One polynomial for one launch day. If you went to the next day, you needed another polynomial. And you can imagine nobody's going to say, let's delay 3 months. So you would develop several polynomials, to try to cover how long you thought it was going to take to lift off. And so that was a problem. Eventually he got it down to about a month, but nobody really thought that was a great idea either. Helmut Horn, who developed the control system for the V-2 rocket in Germany in 1942, was our second level supervisor. There was the way it went as far as the supervision at Huntsville. We had von Braun at the top. We had what we call laboratories. And these laboratories were all Germans from World War II except one, Schillinger, Schlesinger, you name it, on the way across until you finally got to Fred. Fred was the only American at that level. When everybody came to Huntsville to see the Saturn V launch site, and think of it a minute. We had a President Kennedy. When President Kennedy came, von Braun was introduced into the lab heads, and when he got to Fred, he says, "How the hell did you get here?" So down below the lab heads were called departments, and then below that was was that section. And then there were all the workers. And here I was right here. Okay, so right here was Helmut Horn. Helmut Horn had an idea. It had nothing to do with guidance. He thought we had limited computers back then. We only had 2 computers for the entire NASA, and there were 6,000 employees. So every night you had to get priority and special permission to even run a computer case. And so I was very limited. I could make 1 run a night. I had 20 seconds, which was an extraordinary amount of time, actually. I could make 1 run a night to do my analysis. And if I did something, if I had an input wrong on those punch cards, I was down the tubes for that day. So be very careful about the runs that you make and the decisions you make on that. And what Horn thought is he said, you know, suppose, and by the way, we use run the kutta integration, and we calculated every 2 seconds in order to come up with the equation and the flight path to get into orbit, and it had to be minimized for fuel. And so this was the whole process using calculus of variation simulations to apply the minimum fuel path. Well, he said, you know, suppose that we could take the equations of motion for the vehicle and closed form integrate it, and then come up with just a set of equations that could be calculated just like instantly every 2 seconds and get us into orbit with minimum fuel. That would save a tremendous amount of computer time. And instead of taking 20 seconds of computer time, it'd be less than 1 second of computer time. Well, that would be something. And so he floated this idea around, and there was a guy right here named Justin Hart. And Justin Hart had gotten his PhD in math by studying on airplanes as he flew back and forth to California working on Apollo. And when I saw him, when I first went to work here, he looked like an old guy to me. He must have been at least 35. And so he had a heart problem on top of that. So I thought he was 1 foot in the grave, you know. Well, he looked at what Horn wanted to do and immediately saw the possibilities of it being a guidance system instead of just a simulation program. So he put a guy named Gene Smith on the job. And our second level boss was Doris Chandler. And Doris Chandler very quickly became my boss because Hart left. And he was promoted to a department, and he left, and Doris Chandler took over as section head. So she was my boss for 4 years there in Huntsville. And so Gene Smith worked 8 hours a day on this idea of integrating these equations. And so I'm going to show you what they look like. First of all, you start right off with, you look at x double dot, which is acceleration. This is what it represents here. This is acceleration. This is chi pitch. And so therefore the acceleration along the x-axis right here, we can call it a sub x, equals to total acceleration times the cosine of chi pitch. So it's a very simple equation. On the y direction, we can write the same equation, except gravity is going to be straight down our y-axis, and so we subtract gravity. If we take these 2 equations and actually do the integration and solve what chi pitch might look like, go ahead. We come up with this equation right here. And you notice that this is velocity, 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 gravity, and time. Gravity was always a concern. When you go to Earth orbit, there's 2 forces that are going to keep you from getting there. One's gravity, the other's atmosphere. Gravity is 9/10 of it. So you've got to be concerned about gravity. However, this equation right here doesn't take into account any altitude constraint. So you can't put in 100 miles and say that I'm going to get there because there's no place to put it in. This is what we knew in 1960. Our steering equation right now assumes a flat Earth, constant gravity, one-stage rocket, flying in an X-Y direction only, and no altitude enforcement. So you might say we started off kind of small, and we did. Good. So, just like this guy. Go ahead. If we restate the problem is this: we need some sort of a steering law that will get us into orbit with minimum fuel. We need cutoff accuracy. Nobody's going to congratulate us if we miss altitude 5 miles, for example. We need stable equations, no iterations. There were lots of proposals on guidance equations that required an iteration to come to a solution. When you're going to have to issue a command every 2 seconds to the control system and never miss it, you can't be fooling around with trying to make equations converge. So that was out of the question. We're going to fly in 3 dimensions, as I just mentioned. We also have 2 stages that we have to take care of with 10-second separation between them. We're going to have to take care of that mixture ratio shift. And who says that the coordinate system of the inertial platform is the best one to use for the guidance equations? Matter of fact, it was not. What about how are we going to approximate gravity? How are we going to calculate and estimate the time it's going to take to get to orbit, which has to be in the equations? And how big are they going to be? Well, the Dynamics Lab gave us a whole 2,000 bytes of space in the computers. They use it however you want. We're talking about 2,000, not 2 million, not 200,000, 2,000. So with that, and I'll tell the kids, well, at that, we got out our cell phones and we sent a text to Sir Isaac Newton. He got back real quick. He said, F equal MA, I'll leave the details to you. Okay, go ahead. Looking at our simulations, this is what kind of pitch looks like as a function of time. This is the direction, this is time, and this is what kind of pitch looks like. Well, you know, we can immediately look at that and say, you know what? When I was in high school, I learned about an equation that said y equal mx plus b. And that's a straight line. And so our steering equation can look something like mt plus b. And this could be kind of pitch that looks like this. And so armed with that information, go ahead. We can now come up with an equation that looks like this. We can have something that says acceleration equals to F over m times I did here, just simply cosine of A plus B T. Okay, oh, thank you. I was going to get to show you I could still bend over. Now we've got a function of time over here on our kind of pitch, but what about acceleration? Well, there's another way to write this. We could write it as F over our initial weight minus the rate that we burn the fuel times time. And you can see here that when we burn all the fuel, the denominator is going to go to 0, and this whole equation is going to blow up. But that didn't slow us down. You know, we were 25 years old. These small things didn't bother us at all. So let's divide the numerator and denominator by m dot. And as all students know today, F over m dot is equal to the specific impulse of the rocket engine, which can be measured at sea level. It's a measure of horsepower of a rocket engine. And actually, if you use gravity to multiply by this, you come out with what's called VEX, which is the exhaust velocity. And that's what Gene Smith preferred to use, was exhaust velocity. M0 over M dot represents the total time it's going to take to burn all the fuel, so call that tau, and minus t. So we end up with an equation that looks like this. Acceleration equals to Vx divided by tau minus t times the cosine of a plus bt. Now, all we have to do is integrate this once, and what we get is the velocity in the x direction, and we integrate it again, and we get position in the x direction. And then using these equations, and we know the velocity in the x direction and the position, in fact, x, y, z from our inertial platform, and we know the time from a clock, so we can plug those numbers in, and then after we integrate these equations, we can solve simultaneously. And guess what? We're going to solve for A and B. No problem at all. Took Gene Smith over 2 years, 8 hours a day, to figure out how to do that. And this is how he did it. I sat about 20 feet from Gene. And boy, he was a hard worker. Oh, this term right here, you notice this is A plus BT right there. But there's another little term, and that was contributed by Justin Hart right away. He was a mathematician that immediately saw the way to enforce the altitude was to include another term that would be smaller, that would not override the velocity constraint, but it would get the altitude involved. And he came up with the idea of minus K1. So this is the equation I just wrote on the board, but you notice that there's something about this. This cosine function right here has a K2, has a T inside of the cosine. When you start to integrate this function, you're going to start getting big equations that are pretty complicated. And the thing was starting to blow up, and we realized right away, I say we, when I say we, it was Gene Smith. I wasn't even working on this at the time. I was given something else to do. And, but, you know, we played cards every day at lunch for half an hour. So, you know, we talked about it. We were in the same room. There was one room about half this size, and there were like 5 of us. And and every once in a while we get tired of where our desk was, and we just get up and move our desk somewhere else. Pretty simple. And so how could this be changed? Well, the first idea was series expansion. Let's do something like that. Well, that didn't work very well either. And then if you think back to high school trigonometry, you learned this identity right here. And if you realize that this term right here is small, you can take Sir Isaac Newton's idea and just say throw away the small stuff, and what you end up with is this equation right here. And you notice this equation right here has nothing inside the cosine function that's a t. This is cosine of tau pitch, this is K1 sine x, this is K2t, but there's nothing inside that cosine function. These are all 3 separate terms multiplied by the total acceleration here. And so how about that? So Gene worked on that. Go ahead. After 6 or 7 months, you begin to realize there are certain things that reoccur all the time, and that is the integration of acceleration is equal to this. Acceleration twice is equal to this. Acceleration times time is equal to this. The second acceleration times time is equal to this. And this occurs over and over, and so therefore you can just label these A, B, C, D, and you can proceed to cut down the amount of stuff you have to write. Go ahead. In about 1963, starting of 3, Doris Chandler called me in her office and said, we know how we're going to get into Earth orbit now. We got the guidance equations to do that. However, when we get ready to come out of Earth orbit, we're going to looks like this. We're going to come out of Earth orbit, and we're going to go out into space like this. And somewhere in here, we're going to do that second stage burn. And we're going to gain our 10,000 feet per second. And we need to be pointed in the right direction such that the moon over here, which is going around the Earth, 3 days later will be here. And we're going to be 10,000 kilometers in front of the leading edge of the moon after we coast 3 days. We know the Earth is moving around the sun, the whole thing. We're moving in orbit, everything is in motion. And all you have to do is figure out what direction we should be pointed right here. I had not a single clue. You have to remember, at the time I was 25 years old, not too long out of school. Thought I was pretty smart. But when she gave me this problem, I realized how dumb I really was. The first thing I did was I went to the library and found one little publication from JPL, Jet Propulsion Laboratories in California. I got the guy's name, I got on an airplane, flew out there and talked to him, and he was the zero help. The only thing he told me was, we know how to go to Mars and all the planets, but we never thought about going to the moon. So I came back home, and I didn't have a clue what to do. The only thing I really need to do, I read a book in high school called How to Solve It. And it said, if you don't know how to solve something, go ahead and work on stuff that you know how to solve, and then maybe something will come to you. And that's what I did. I knew that I had to have a simulation that would run this situation. I was using calculus of variation here to get an optimum burn here in order to meet this criteria. But I'd never used the guidance equations, so I needed Gene Smith's guidance equations right here. These were called IGM, iterative guidance mode by that time. And I needed IGM equations here such that I could have the guidance equations do the burn and then point this thing. And I knew the vector here it was supposed to be at. So I could use that as my end condition that came from the calculation of calculus of variations. And then I could use IGM to do this steering and actually fly this trajectory, which looked pretty good. But where was this going to come from? It couldn't come from calculus of variations. It had to be something else. And something else in my mind meant that it had to be an analytic solution just like IGM. It had to be something that could be programmed in the onboard computer, and it had to be analytic like IGM was. If it wasn't, these equations would never fly the Saturn V. And by the way, across the hall, Dr. Hopper was just chomping at the bit, convinced that he had it in the bag, and we had no chance whatsoever. He had like 30 people, several PhD mathematicians. There were 4 or 5 of us. Nobody took him, I guarantee you, nobody took somebody from Oklahoma Baptist University seriously. And yet I was assigned to work on this problem. Well, why was I assigned to work on it? I found out years later when John Goodman got involved, and some of y'all have read his paper, a historian, and he started asking me about what we did back then. And he started doing research. He found out that Justin Hart, once he was given a promotion to department head, he had let out 3 contracts to 3 universities, University of Alabama, Georgia Tech, and University of Alabama, to work on this problem. And after 6 months, they'd come up with 0. Didn't have a clue. And so he turned around to Doris Chandler and said, I don't know what we're going to do because nobody is coming up with this. So she called me in her office and said, I want you to work on it. Why she decided on me, I have no idea, but she did. And so here I was, Well, I needed the equations, like I say, to get out of Earth orbit. And so I rolled my chair over to Gene's desk and he handed me this handwritten piece of document. He had already gone through these and reproduced them again on another document. It was 45 pages long. I have to say that I have it in my desk drawer at home. And this is what his handwriting looked like at the time. Here you can see there's an E and there's a BEX1 for the first stage, time to burn for the first stage. You can see the intervals, and then you can see the 2 for the second stage, and so on. And this is on page 21 of page 45. So what does the result look like? When you take a look at K1, it's B1 times C2. Here is B1. Here is C2 right here. Here is A2 times B1. A2 is this equation times B1, which is this equation right here, minus A1, which is this equation, times B2, which is the biggest equation on this board right here, three rows. Now, this is not a simple equation. These are not simple equations. Could this possibly work? There was great doubt. My Wayne Deaton, who worked about 15 feet away, was given the assignment to study the performance of the Saturn V, run all the cases, all the perturbations that could go wrong, all the different weights, time of liftoff, you name it, out of plane, and determine how good these equations would really work under conditions that were similar to what might happen. Wayne Deaton had two big qualifications. He had gone through nuclear energy school for the Navy before he came to work for NASA, and he was my doubles tennis partner. We played tennis. We played doubles together on the Huntsville tennis team. He was the guy that asked me if I'd like to work for NASA. That's how I ended up here. Go ahead. So, I was on the guidance subcommittee, and every other month we would meet either in Houston or Huntsville, and we'd fly back and forth every other month. And so Doris came to me and she said, I need for you to go to Houston and make a presentation on how we're going to fly the Saturn V. And so I made 2 flow charts. This was the first one. This shows the ascent guidance itself in a flow chart form that has the coordinate transformations, the calculations before it ignites, and then the calculation of chi pitch and chi yaw. By the way, when Gene changed the coordinate systems from the inertial platform to a platform at estimated cutoff, it reduced the number of equations. And that's what this represents right here. And so the final result is we have all these things to look at. Okay. Okay. We have I mentioned a new coordinate system. We need minimum fuel. We need cutoff accuracy. Dynamic laboratory. They were the final say-so. We gave them our equations and they put them in their computers. They ran simulations and they could say yes or no. That they had absolute authority. They were responsible for the integrity of the vehicle. If anything broke it apart, some stupid commands, some guidance was sent to the control system, they could reject it. They were the final say-so. We had to get their approval. And finally, we had a complete analytic solution that they signed off on. Nobody had told us yet we were going to fly the Saturn V. Remember, we were just developing software. So how good did it work? It came within 0.1% of minimum fuel. Altitude was 4 inches off out of 100 miles. Our velocity was off 0.03 feet per second out of 25,000 feet per second. We were, our angle getting into the right plane was off 1/1000th of a degree. Now we're going to have additional errors due to hardware, which we simulated also. I ran 6 degree of freedom simulations. This is an actual case of Apollo 13. The S2 engine went out, and when it did, we burned 0.04% more fuel than optimum. We were 30 feet high out of 100 miles, and our velocity was 2 feet per second low out of 35,000 feet per second, or 25,000 feet per second. It took us 44 seconds longer to reach orbit than if that engine hadn't gone out. when we did our translunar insertion burn, at the end of that burn, we were off 12 feet per second too fast out of 35,000 feet per second. We were out of plane by 0.016 degrees. And our mid-course correction, the first one was 22 feet per second. This is the largest mid-course correction that was ever done on Apollo. And only the first one was ever done. Go ahead. This is Gene Smith's paper, written in 1965 with the initial set of guidance equations, TMX 53258, Isaac E. Smith. Go ahead. This is on the internet, by the way, in NASA archives. Go ahead. So the targeting, well, I still was stumped. And one day I came back from lunch, and I went by Dr. Hoepner's area, and there was a guy sitting there eating potato chips. And I looked up at the wall, and there was this big drawing that looked kind of like this. It was an ellipsoid, except the lines were horizontal. I didn't know how to do that on the computer. And they were horizontal. And I said, what is that? And he goes, that's a representation of all of the trajectories that go to the moon with a 72-hour flight time. And I said, well, what are those lines? And he said, those are different launch azimuths. And the light came on. Almost yelled eureka. I ran back to my office. I mean, I literally ran down the hall to my office, and I went in. I saw Dan Martin, one of the guys in the second. I said, Dan, I know how we're going to get to the moon. And I drew a diagram. It looked just about like this. It was pretty crude, but it looked like this. It was had this ellipsoid like this, and here was the Earth here, and here was the vector right here. This is the vector, acceleration vector, and this is tangent to this ellipsoid. And all you have to do is come out of Earth orbit and cut off on this ellipsoid according to the launch azimuth, and you're going to get to the moon on this path, and you can totally predict that path. And amazingly enough, there was a report that was written by Dr. Hoepner's group 2 years before that made a comment, and it was all calculus of variation type stuff. But there was one little paragraph that had a comment that it might be possible to take these parameters and come up with an analytic solution for lunar targeting. And that was it. I never saw that report. It came out in July of '62. And what happened in July of '62? July the 4th, 1962 weekend, NASA headquarters building, the first building that NASA built at Redstone Arsenal, was completed, and we were moved, lock, stock, and barrel, from the Army headquarters building to NASA building. We put everything in boxes, labeled where we were going, went home, and after the weekend we came back, and there the boxes were sitting in our area. In some way, that report, which I was on the distribution, I never saw. I don't know how many other people didn't see it, but I never saw it. I never saw that line. I don't know what I would have done with it at the time anyway. I forgot about it. But anyway, Dr. Hoepner had the solution right in front of him, but he had absolute blinders on. Calculus of variations was the way to go. That was it. So anyway, go ahead. So here are the variables. The target vector where we want to be pointed. We have the angle between the target vector and perigee of the ellipse, and we have the energy at cutoff, and we have the eccentricity of the ellipse. And I had taken solid geometry in high school, so I understood a little bit about solid geometry. Go ahead. The guy that wrote the paper, Goodman, came up with this, and I about fell over when he emailed it to me. One day, George Chandler came to me and said, I need for you to write down the hypersurface equations, which we call them, for the targeting, and give them to me as quick as you can, preferably today. So I sat down on my desk and I wrote them out on 2 pieces of paper. And this was one of the pieces of paper. And this is my handwriting. I couldn't believe it. I mean, somebody had actually made a copy of this and put it in the NASA archives. And this is what it looked like back then. Go ahead. So this is what it looked like in my report. There's the target vector. And you can see they're all vectors. So that was the idea. Use vectors to get on that hyper, to get on that ellipsoid. And calculate these vectors. Go ahead. And so this is the flow chart I showed at Johnson. These are the initial conditions here. This is what you compute just prior to ignition, and then you do this, and then you get your inputs from your inertial platform, and you come up and you put your guidance equations right here. That whole flow chart that I first showed you fits in that little box right there, and then you cut off when your energy is correct. And that's how you fly to that vector. Okay. So, this is a picture of the cover page of my document, which actually has my name right down here, in 1965. This became the defining document for the targeting for the Saturn V. It was presented to NASA headquarters by Werner von Braun himself, and they took it and gave it to a company called Belcom, which spent a year studying it and came up to the conclusion that it would actually work. And it was programmed in the onboard computer and flew all the Saturn V vehicles. Go ahead. So, how would all this take? Well, Helmut I mentioned 1960. Smith, Hart, and Chandler started working on it, and it took them 2.5 years to come up with the initial integration formulation. And then Gene Smith and Wayne Deaton did the 3-dimensional version. Took them another year. And then I wrote my report in May of '65. It took me 1.7 years to come up with the targeting equations. And very shortly after that, it was approved as the official way that we were going to fly the Saturn V. There were a series of meetings and analysis and people arguing one way or another for calculus variation versus IGM and this. But it was decided that our method would work. And then Belcom came out in 1966 and approved the targeting. And Apollo 8 was the first mission that it flew on, the one that went around the moon. John Goodman called me up 56 years later and said, "Could you tell me in detail exactly how all this stuff was done?" And I started thinking and writing and thinking and looking stuff up. And this is the best I can come up with. This is Wayne Deaton, my doubles partner. And there I am on the tennis courts in Huntsville, Alabama. Only picture I have of Wayne. They wouldn't allow us to take the camera on Redstone Arsenal. It was an Army base, and there were lots of Army headquarters there with different projects, and they did not allow cameras. Okay, well, that is my summary of the guidance equations for the Saturn V. Yes.
So, we don't know, as you said, Werner Braun was in charge of the project, I'm assuming all the time at the time. Did he really get the mathematics, or did he have a different angle on it? Did he have a different involvement in the project, or did he understand the mathematics that you provided?
Who's that?
Von Braun. Did he
Von
understand?
Braun. Oh yeah, he understood it, yeah.
Okay.
Yeah, there's no doubt. Von Braun was a brilliant guy. Really was. Wayne Deaton, I found out later, many years later. Every time I go through Huntsville, I stop by and see Wayne. I bought a lot across from his house. I was gonna build a house across from his, and we were gonna build a tennis court to teach our kids to play tennis. That was our plan. And I ended up coming to Houston, and it's like, the old movie called Heaven Can Wait. There's a scene in there where the owner of the Los Angeles Rams sells his football team to this guy that knew nothing about football, but he had a lot of money. And so he said, "How could you sell the team?" And he goes, "For the grossest of reasons." And he says, what's that? And he says, he offered me a lot of money. That's why I came to Houston. GRW in Houston could afford to pay me almost double what NASA could pay me. And I could see my ability to go up the ladder a little bit in Huntsville was very limited. Because at the same time, Apollo was going to be going down and people were going to be laid off. And so if you're in a company that's laying off people, what chance are you going to have to get promoted, you know? So I said, and plus I knew a lot of people that were smarter than I was. So, you know, it wasn't a gigantic decision other than leaving Huntsville and Wayne and our plans. But that's how I ended up in Houston. And by the way, that's how there were 5 of us and 3 of us left for the same reason. One went to Boeing, Gene Smith went to Boeing, another one went to Northrop, and I came to Houston CRW. So, and we were pretty valuable people because there were only 4 of us that really knew about the guys that played on the Saturn V, and these were contractors that wrote substantial contracts and made a lot of money off of us. I didn't know that at the time. I was too young to understand how that worked. Yeah, when I got to Houston, the first thing I did was develop another simulation for Johnson Center so that they could run studies and analyze it, explain to them how it worked, because they didn't have a clue.
So Apollo 8 was like the first big test.
That was the first one that flew these equations we're talking about, and every other one after that.
Yeah. Were there any of the equations adapted for things for like the Surveyor and Ranger missions?
Oh, that's a good question. There was a guy that came over at one time when I was working on the targeting, named Roland Jaggers. And he came from Faulkner's group, and he was sent over to help me. I say over, across the hall. And he was configuration 1,000%. And we butted heads right off the bat because he wanted a calculus variation solution for the targeting. I wanted an analytic solution. I went to Doris and I told her, I said, you know, this isn't working. She said, you don't have to do anything Roland tells you. Well, boy, that was a revelation, I tell you, it really was. And shortly thereafter, he disappeared, went back across the hall. After Apollo, some years later, Roland came up with the idea of the PEG guidance system, PEG. And PEG is what flew the shuttle. He was a very smart guy, and he used calculus variations to come up with the PEG guidance system that flew the shuttle vehicle for 20 years. I never really held that against him. I just felt like he was going the wrong direction, you know, back then. But I knew he was smart.
We have a question online. Ari said it looks like much of the science was done in non-metric units. Was that a conscious decision?
In Huntsville, Alabama, run by the Germans, everything was metric. MKS system, 100%. Just like in college, just like in high school, everything was metric. Everything in Houston was English. Not only English, nautical miles. I mean, we're talking about 100 nautical miles. I said miles, but it's really 100 nautical miles. I mean, on the trajectories that I would print out and bring to Houston, I had 2 blocks to print out. One was in metric, the second one was in the units that Johnson used. And so when I opened them up, and we would look at them, everybody in Houston would look at one block, and I would look at the other block and try to visualize in my mind what we were talking about. I mean, instead of 185.2 kilometers, it was 100 nautical miles.
When they go back to the moon, do you think they're going to use your same equations?
No.
Different ones?
Yeah, the reason why is the primary limitation of the Saturn V equation is the length of the arc going into orbit. And as that arc gets bigger, it gets harder to estimate the time of burn of the vehicle as it goes across the Earth or into orbit or whatever it's going to do. That's a real limitation, and the latest guidance equations like egg overcome that, and that's why they're the future. And Dr. Dukeman, I've corresponded with him some at Marshall Space Flight Center right now. He's in charge of the equations for the SLS, and they're using a completely different way to do the Gauss equation. Everything changes, everything progresses.
As far as the computer that was on board, what was the memory capacity of that computer?
I don't remember. You can get on the internet and look. I don't remember the total thing, but our allocation was fairly small. As you can imagine, the dynamics lab was pretty big.
I think it was very limited back then.
They controlled it all. Yeah, they were the people. Wayne did, I mentioned, we worked together in the guidance section. His brother worked in the dynamics lab. And every once in a while, his brother would come over to eat lunch with Wayne. And so we had a path through the dynamics lab that most people didn't have. We got to learn a little bit about the way they thought. And so we could tailor our stuff to make sure they understood what we were up to. That was a big plus. Terrell was a good guy.
I have a question, but thanks for the presentation. This was excellent. It is humbling to see the equations that took humanity to the moon. Right, this is really humbling. I posted the question on the chat. So I see most of the units that we used were non-metric. Was that a conscious decision that was done to use non-metric units?
The units used on the shuttle?
Yeah,
He posted the question on the chat.
yeah, you might have missed it. We answered that, Ari, but if you wanted, it's the same question we just asked about the units.
I'm not surprised that the shuttle equations were primarily English units, because that's what Johnson said. To me, that was a great change. NASA was looked at as the leading technology people in the world. Why they didn't insist, NASA headquarters didn't say we're going to use metric, I don't know. But they didn't. They left them under the astronauts is what really happened. You remember in the Right Stuff movie when John Glenn stood up and said, "You're not going to tell us we're going to fly this vehicle"? Well, what that ultimately boiled down to was the Navy guy wanted nautical miles, so they used nautical miles. Another guy wanted to use miles, they used miles. Somebody else wanted to use feet per second, so they used feet per second. We didn't have any choice at Marshall. Bob Brown said metric, and that was it, the beginning and the end.
Yeah, thank you for that. Sorry about. Thank you. Appreciate it.
Next slide. All right, thank you, Don. It's always a pleasure to have you here.
Thank you.